So this is joint work with Bas Luttig, Tim Willemsen, and Wouter Scholz. Wouter Scholz is a master student that worked on this for a bit as well. Can you all see my screen now? All right.
Yeah, it works fine. Yeah, we can see it.
Great. So we'll first dive into a tiny bit of the motivation. Why would you actually want global variables, and also what type of global variables? Then we'll introduce a process algebra that actually uses these global variables, and move on to an accompanying logic, and showcase how you can actually do model checking using existing tools. So first of all, typically in process algebras, you don't really have a concept of a global state. You simply have a process expression with possibly parallel components that communicate via message passing. So if one of the parallel components wants to know something from another parallel component, it first needs to communicate, and then it has this piece of information. But sometimes this is a bit inconvenient. So I do a lot of research in train management systems. And this is something I encountered in practice. You have this train that is moving towards a point or a switch. And these points or switches, they are different parallel components to this train. And somehow this train needs to do a move forward action and end up in, well, either these crushing these 5 people or this one person. So in a way, you need to decide as a train which section you go to. But the problem is you don't know the current position of the point. And so some way you need to get this position and then do the move. But you have the risk that once you've gotten the position of the point, that it's updated and no longer current, no longer relevant. So in this practical example, I was able to kind of use a workaround, but it did motivate me to see how we can actually improve this so that you can model things better. I will go into a bit more detail of another example. So suppose that we have a traffic light controller and a car, and this traffic light controller controls just a single traffic light and can set it to green or red. And we have a car that can drive or it can brake. So we have kind of 2 scenarios. Either the car is lucky and it can just drive right through over the junction, or it first needs to brake and then it can drive once the light is green again. So what we want is a label transition system that looks something like this. So if on the top row of states, the light is green and the car is free to go, but possibly it first changes to red, the car brakes, and it needs to wait for green again. And in the end, you always have that the car crosses the junction. But how would you actually model this in standard process algebras? One way would be to just remove the parallelism, to just have one process that both performs the car action, so the drive and the brake, and changes the traffic lights. But that's kind of inelegant, and if you have a large number of parallel components, this becomes kind of tedious because you would need to do the linearization by hand. You could also think of something like a protocol locking the value, so that when the car wants to cross, it first locks some value, reads it, and decides whether it brakes or drives. But this introduces extra steps in the LTS, so you don't really want to do this. Or the workaround that I actually used for these trains is that if you have a communication function in your process algebra that is a bit more advanced, then you can say, well, the traffic light controller has a signal green action, and the car can do a drive if green action. And if they can both do these actions, then they communicate to the drive. So then in the LTS, you would simply have the drive, and it can only happen if the traffic light is actually green. But this is still somewhat inelegant. Suppose that you have another car that is actually willing to drive through a red traffic light, then you would need to change this communication function to accommodate that you can also drive if the light is red. And you're kind of mixing sending information and deciding what to do on the information. So you would like to separate this, and you could separate it into global variables that you can access instantly. So we'll see how we can do this in a process algebra. So suppose that we have a finite set of global variables, called var, and some possibly infinite data domain D. And we can have normal action labels like drive and brake, but we also have special assign labels, which have as parameters a variable name, so the v, and a data value. And we define a process algebra with these operators. So we have a prefix, and this lambda can be both an action label or a special assign action. We have an in action, so that's similar to the zero process in some other process algebras. We have simply a choice, parallel composition of processes, encapsulation. So if there's an action in this set B, then you can block it and you can use it to enforce communication. I'll get back to communication in a bit. We have recursion, so you can have a recursion variable x and accompanying defining equations. And most interestingly, we can have a conditional. So here again, the v is a name of a variable and the d is a data element. So we can use this conditional to specify if variable v has data value d, then we are allowed to do some action from p. So the first observation here is that states do not only contain a process expression, but also a valuation. So this is simply a mapping from the set of variables to the data domain. And if we have an assign action, then this mapping is updated. Simple as that. So this notation on the right is the mapping v, where v, the small v, is updated to the new value d. And the conditional has the following semantics. So if the process P can do a let the action to P prime, then with the conditional, it can do this action only if the mapping V actually maps the variable to the correct data element. And to quickly go back to communication, we have this ACP style communication function. So we can define a communication, for example, A and B map to C. And if two parallel components can do an A and a B, then you can actually do a C. And these A, B, and C's are not allowed to be assign actions, because it'd be kind of weird to have two assign actions that communicate to something else. Would be unclear what the semantics of that would be. All right, so let's get back to the traffic light example. So we have a data domain of two elements, green and red. And we define a recursive specification for the car and the traffic light controller. The car, if the traffic light is green, it can drive, or when it's red, it brakes, and then when it's green again, it drives. The traffic light controller is even simpler. If the light is green, it can turn into red. If it's red, it can turn into green. So then the initial state is the parallel composition of the car and the traffic light controller with evaluation, and we can pick it to be green at the start. And then we actually get the LTS that we were looking for, modulo the exact names of some of the labels. And we were able to do this with actual parallel components, with an intuitive way of using this global variable. And if you would want to add a second car that does want to drive through a red light, then that would be very easy. You could just add another car that has a condition, if T is red, then also drive. Then this may be why these global states are not already baked into process algebras. It's more difficult to define good equivalence relations. So in particular, strong bisimilarity is not a congruence. So if we have a mapping that maps this small v to 0, then for these two process expressions, they can just both do an A. As well, it happens to be that v is 0 is true. So the top one can do an A action, and the bottom one can do an A action for any value. So it can also do an A action. But for example, if we use a prefix with an assign that updates the v to 1, then they are no longer equivalent. So this, yeah, it's kind of annoying. So let's have a look at other equivalence relations that we might want to use. So we already concluded that strong bisimilarity is not a congruence. It is a relation on states. And the valuation does not play any role in how strong bisimilarity is defined. Strong bisimilarity only looks at the labels on transitions and not at the states. We can also define state-based bisimilarity. So that's also defined on states, but it has the additional requirement that the states that you compare, that the valuation is exactly the same. Unfortunately, this is still not a congruence because it suffers from the same problem we saw earlier. But it has the benefit that you can at least compare the valuation, which is, for example, useful if this valuation is visible from the environment. We also have stateless bisimilarity. This is a congruence. This is not a relation on states, but on processes. And the valuation is quantified. So if we have processes P and Q, then we say they are stateless bisimilar if for all valuations they can make the same step, say to P prime and Q prime. And then for P prime and Q prime, we again quantify over all valuations that they can make the same step. So in essence, in all contexts that may change the global variables, they behave exactly the same. I could have, at first I had the exact definitions on the slides, but that's kind of tedious. If you want to dive into what these equivalence relations, how they are defined exactly, you should just read our paper, which I recommend anyhow. So onto our first real contribution. We have defined an extension for the Hennessy-Newton logic with two new operators. So the first one is a check operator. So this V is E, which is, if we look at the semantics, is true for any state in the universe that maps, where the valuation maps V to E. And the second operator is a bit weird in a sense. It sets the value of a variable to this E. So if you look at the semantics, then it's true for any states in the universe where the process expression is the same, and then the valuation is updated. So as a kind of an example, if we have, from the previous example, if we have these two process expressions, one can only do an A action when V is 0, and the other can do an A action always, then we can differentiate them with this set operator by saying, well, we set the valuation to 1, and then A true is only true for the one that can always do the A action. So this is kind of a way to check for all valuations what the behavior is, and even for valuations that are not reachable from an initial state. So we've been able to show a nice correspondence between the process algebra and the logic. My apologies for the wall of text, but I wanted to spell this out more exactly. So if you have process expressions P and Q, and we require that these two are image finite, again, read the paper if you want to know exactly what we mean by image finite process expressions. Then they are stateless bisimilar. So this is the SL in the bisimulation relation. If and only if, for all valuations, they satisfy the same check and set formulas. And also the other way around, if they have the same, they satisfy the same check, HML check and set formulas, then they are actually bisimilar. Or in other words, if they are not bisimilar, we can always find an equation that, or a formula that differentiates them. We have a similar correspondence for state-based bisimilarity and HML check formulas. So this is without the set operator. Here we have that if they are two states are state-based bisimilar, then they satisfy the same formulas, and the other way around. So intuitively, state-based bisimilarity doesn't quantify over all the valuations. It just looks at only the reachable states. So we don't want to have this set operator, but for stateless bisimilarity, we need this set operator to reason about states that are not necessarily reachable. We've defined a translation to MCL2, so we can do model checking for this process algebra with global variables. But to explain the translation, I first need to explain how multi-actions work in MCL2. So I'll do that hopefully a bit quickly. So if we have this process expression with a parallel operator, the left side can do a multi-action of an A action and a B action. So this means they can be jointly executed. And the right side can simply do a C. And this process expressions can either do an A and a B together. It can do a C together, a C on its own, or it can do the A, B, and C in one step. And we can manipulate these multi-actions with a communication operator. So if we define a communication A and C to D, then the multi-action of these three will combine the A and the C to a D. And this communication only happens when the parameters of the actions match exactly. So if this 2 of the A would be a 3, then the A and the C can't communicate because they don't have the same data values. We can also hide actions. So if we hide the A in this multi-action, then, well, you remove it simply. And because with these multi-actions, you can have kind of an explosion of all kinds of combinations of actions. MSL2 doesn't feature a block, though I think it might also feature a block, but we also have an allow operator that only allows the actions that are in the set. So if we only allow A, then a multi-action with A and other things is not allowed. On to how we translate these conditionals. We have an extra process that tracks the global variables. And this globs process can contribute a check G action, where the D is the current value of the variable. So we define this translation for the case that we have one global variable, and in the paper we also give hints on how to extend it to any number of global variables. And the second parameter is simply true. And anywhere where we have a conditional, we translate it to this cryptic statement. So we have a sum here that sums over all the values in the data domain, which is put in the first parameter. And we have here the condition that is kind of reflected from the left. So if V is D, then we check that this D1 is actually equal to the D. Oh, and of course we have the A action that we want. In the communication operator, we define that check G and check P communicate to check. And as we mentioned, they can only communicate if the parameters match exactly. So that means that this second parameter must be true. So under the hood, MSL2 will evaluate the D1 is D, and they can only communicate when that is true. And we hide the check, so that we only have the A left, and we allow the A and possibly other action labels. In the case that you are more confused and enlightened by this explanation, the main takeaway is that we use these multi-actions to, in one step, check the value of the global variable and do the action on which it depends. We also translate HTML check formulas, so without the set operator. To do this, we add self loops to the globs process. So it has a self loop with a value label with, well, the current value of the variable. And we translate the HTML check formula by replacing the check with this. So this will be only be true if this self loop is present. And the result is that we can actually check these formulas after translation. So we prove in the paper that the original formula is true for the original process expression if and only if the translated formula holds for the encoding in MSL2. So in summary, we introduced the process algebra with these global variables, and we looked at some appropriate equivalences. And then the first contribution is extension of Hennessy-Miller logic, so we can differentiate them, and a translation to MSL2. What we plan on working on in the future is to actually not use these global variables in some made-up process algebra, but to actually extend MSOL2 with global variables, and perhaps use shared variables so that we can have a scope attached to a variable. That's it from my side. If you have any questions, feel free to ask.